Welcome to qnawire.
All right, so what we have here in this problem is a chicken gun, and we know the location of the chicken as a function of time. So this is a calculus-based problem, and then we're given that explicit formula. So we'll be able to use calculus and specifically derivatives in order, sorry, that's just two significant figures, use calculus in order to find both the velocity and accelerations of this chicken as functions of time. So let me just go ahead and finish writing out this analytic expression, oops, that is given to us 8.0 times 10 to the fourth times time cubed. Okay, so we basically have a third order polynomial, and we want to know how long the gun barrel needs to be. In other words, what distance does the chicken need to accelerate over if the duration of the acceleration was 25 milliseconds. So what that means is that since we have general expression for position as a function of time, we just need to go ahead and plug in 25 milliseconds or 0.025 seconds in SI, and then calculate what that value is going to be. So this is a little painful to write out, but I'll do it anyway. We have 9 times 10 to the third power, and then omitting the units here, 0.025 squared, don't forget the square. The same coefficient we had before, 8.0 times 10 to the fourth, and then 25 milliseconds, I'll just call it that, this time cubed. So we go ahead and plug that into a calculator, and at the end of the day, for significant figures, we see that this acceleration would take place over 4.4 meters. So that's how long your chicken gun needs to be, and that does sound kind of long, 4 meters. But remember that this is for airplane testing. They're accelerating the chickens to very, very high velocities, as we'll see, in order to test them. So it's not surprising that these need to be industrial grade guns. So the next part, we want to know what velocity the chicken will be moving at by the time it exits that 4.4 meter barrel. So we'll need to solve, in other words, for the velocity in general as a function of time, specifically at 0.025 seconds. But first of all, we got to do velocity as a function of time. So we need to take the first derivative of x with respect to time. In other words, finding x prime. So we just use the power rule, the chain rule, for solving for that. So for dealing with the hopefully we all have good calculus skills, but dealing with the t squared term, the 2 jumps out in front, so we get 1.8 times 10 to the fourth. T to the single power, we decrease the exponent by 1, and over here we get 8 times 3, so 24, or in scientific notation, 2.4 times 10 to the fifth, and then get a t squared over here. So that's what velocity is in general as a function of time. And now we're going to go ahead and plug in that very specific 25 milliseconds again. Sorry. Oops. 25 milliseconds. Plug in those values. So we have new coefficients now. That's 1.8 times 10 to the fourth being multiplied by 0.025. And then 0.025 quantity squared, plug that into a calculator, and then get exactly 300 meters per second. So these chickens are going fast. Okay, so we're going to take this one step further and find what we're really after is the force. But in order to do that, we need to find the acceleration. Find the acceleration. Sorry, I meant to add a new slide. In part C, so I'm going to break this down into part C, part lowercase Roman numeral number 1. So we'll get to the force in a second, but first let's find the acceleration. So just like how we did it before, acceleration is the first derivative of velocity, or even going a little bit one step further back, the second derivative of position with respect to time. So we can do that since we know the formula from before. So this just becomes 1.8 times 10 to the 4th. Still a minus sign. And then over here we get 4.8 times 10 to the 5th as our coefficients. And then t, just a single t. Okay, so now we want to know what the initial acceleration was. In other words, acceleration at time is equal to 0. And really, I should have put the Roman numeral 1 down here, because this is where the actual number 1 or part 1 starts. So acceleration at time t equals 0. So just plug it into the expression we just found. The second term basically just disappears, and we're left over with 1.8 times 10 to the 4th meters per square second. But what we're really after is the force. So we now apply Newton's second law. So the force at time t equals 0 is equal to mass times acceleration at time t equals 0. And that is 1.50 kilograms is the mass that we're told of the chicken, or the test chicken. 1.8 times 10 to the 4th. And then just for illumination, let's not express our final answer in scientific notation, just so that we can appreciate the magnitude. And we get 27,000 newtons is how strong the force starts off when the chicken is at the beginning side of the barrel. So, as you might have guessed, in part 2, we're going to take a look at the flip side and see what the acceleration is at the very, very end of the barrel, just before the chicken emerges. So we're going to need our friend of 25 milliseconds one more time. Plug that into the expression we found earlier, which was 1.8 times 10 to the 4th minus 4.8 times 10 to the 5th. Plug in that time interval, and then get numerically 6,000 meters per square second. And then do the same thing we did earlier. I'm going to use a little bit of shorthand. F is equal to ma, but specifically at 25 milliseconds. Go ahead and plug that in. 1.50 and then 6,000 for our acceleration to get a force of 9,000 newtons. So the force, or the acceleration rather, decreases as the chicken goes through the barrel. And we're finally done.